Okay everyone, welcome back. So today I'll be going through all 4 problems from day 1 of the NICE Olympiad. If you want to learn more about NICE, the website is nicecontest.xyz. This is a contest where a lot of problems are proposed by my students, though not all. For example, problem 4 is not by one of my students. Okay, so let's get started. So problem 1, there's a sequence that's defined by a1 equals a2 equals 1, and then insert like this long recursion thing. So let me pull up a board so I can write. Alright, so for example, so a1 is equal to 1, a2 is equal to 1, and then a3 is supposed to be equal to, so let's see, 2 is even, so this should be 1 plus 1 is equal to 2. A4 is supposed to be equal to 1 over the previous 2, so 1 over 1 plus 1 over 2, which is equal to 2/3. And A5 is supposed to be equal to the sum of the previous 2, so that's 8/3. And A6 is then equal to 1 over 3/2 plus 3/8, which you can do the calculation, and this will come out to 8 over 15. And so on. So this is what the sequence is. Okay, so yeah, the sort of idea is like, I've just got to claim the sequence as a closed form, and you can sort of guess the closed form by looking at the ratio between consecutive terms. But claim an is given exactly by the following formula. For n even, it is the product of 2 through 4 up to n minus 2 divided by 1 times 3 up to n minus 1. Whereas when n is odd, it's given by what sort of looks similar. I'm writing it a little weird way, but it's okay. It's the evens again on the odds. And you can see this already in the first few examples. 2, 2/3, 8/3, 8/15. This is your 2 times 4 over 1 times 3, and this is 2 times 4, 1 times 3 times 5. Okay, cool. And this is true. So because it's true, it's easy to prove. Induction. Yeah, you plug it in, throw induction at it, and it has to work because it's like, well, that's what it is. Okay, great. So now we know what the sequence is, and the extraction is that it's focused on the numerator of the ANs. It wants the numerator to be a power of 2. So in other words, you would like the VP of numerator to be less than or equal to the VP of denominator for every odd prime p. However, this is actually pretty obvious because when I can take the numerator and I can write it as like this numerator is equal to 2 to the stuff times 1 times 2 times 3 up to n minus 2 over 2, and this is like 2 to the something times 1 times 2 up to n minus 1 over 2. And so the VPs here, the number of multiples of any particular odd prime or prime power will be less than the top bottom. So let me just say that a little more carefully. So claim for any prime power q, the number of multiples of q in numerator is less than or equal to the number of multiples of q in the denominator. And that's because in the denominator, the multiple of q appears earlier, but after that, everything is spaced out exactly by q. Okay, so that will prove it. And yeah, that just works. Shout out to Mew Yu from Juno is a Frog. Every odd multiple appears to the denominator. Is that true? Just due to the 2n. No, because that requires you to actually calculate. Oh, okay. Twitch chat is telling me that you can also do this explicitly. In one case, this fraction is equal to. Someone just tell me what it is. Which one is 2n choose n and which one is. So this one is 2 to the something over 2n.
It should be 2 to the 2n divided by 2n choose n, and then you should just simplify and you're good.
2 to the 2n over 2n choose n? Okay. I don't know. This is one of them and the other one is some variant of it. I don't particularly care about the closed form because like the VP, like sort of for VP reasons, it's pretty clear what's going on anyways. And it's sort of implicitly really proving that it's like power of 2 divided by odd integer and whatever. Okay, so I'm gonna leave problem 1 at that. Anything the nice committee wants to say about the problem? I know that some of the problem authors are in the voice call right now.
One comment from the author was like the name of the sequence actually comes by attempting to flip the last half of the word Fibonacci, but spelling is hard and
yeah, I heard about that. The spell check won't pick that up, huh? Shout out to Blake Couch for making great books from Geico Lizard. Fibbo icon. Okay, cool. Let's do problem 2. So in this is a pretty quick geo. What I'm going to first do is I want to let me draw this picture. So here I have let's say triangle ABC. Yes, center O. All right, and then do this. I draw this perpendicular bisector. I draw this perpendicular bisector. That's ADE. And the question is asking like, how many times can ADE intersect with the line BC? Okay, so the nicest solution to this problem is based on power of a point. Let me first say what the idea is. I'm gonna draw these two things. When I do so, I get a ton of similar triangles. This isosceles triangle is similar to that isosceles triangle. So because of these similar angles, it follows that BD times BA is equal to BO squared. Okay, and then similarly, if I do the same reasoning, CD times CA is also equal to CO squared. Okay, so I want to do a power of a point statement, but I want to be a little bit careful because of possible configuration issues. So I will quickly make a side remark, which is that if I just look at BO, and so here's B, here's O, and this perpendicular bisector, for any point on the circle, regardless of where A is, B will always be outside the segment AD. So A and D can come in either order, like here or here, but it will always be the case that like BD and BA are pointing in the same direction. Okay, cool. So because of this, I can apply a power of a point properly and get the following claim. Actually, I'll type the claim. It's fast in handwriting it. Claim BC is the radical axis of the circumcircle of ADE, and the circle centered at O with radius 0. Unconditionally. This is always true. And so now the question is like, okay, well, what does that tell you about the intersections? So if you imagine ADE, there's a couple cases. If O is in here, the radical axis is here, so they don't meet. This picture's a little bad. If O is out here, the radical axis looks like this, so they don't meet. If O is on the circle, then they do meet at exactly 1 point. So there is certainly at most one intersection point, and equality occurs exactly if ADOE is cyclic. So the question is then, when is ADOE cyclic? And the answer is that whenever the triangle is a right triangle, ADOE will be a rectangle. What happened? Can you explain why BD times BA is equal to BO squared? It's because of the similar triangles. Like, this angle, this angle. Let me draw these properly. This angle, this angle, this angle gives you a pair of similar triangles that will imply that length relation. One angle is right. Okay, so that's it. Okay, we're done. All right. That sound effect is louder than I remember it being. I need to change the volume setting on the noisemaker. Was P3 just loss of case passing? No, not really. Okay, so let's do problem 3 then. So, so problem 3 is some combo problem. It's a parity problem though, where I have a hexagonal grid. Dare you to play 187. What is 187? It's probably copyrighted though. Yeah, I'm making a mistake. Okay, I will not play it. It sounds like it's a mistake. Okay, so you have a hexagonal loop. Let me just draw like an example. Oh crap, drawing hexagons is really hard. Oh my god. Not cool. Who did that? Okay. Sorry, one moment please. I need to edit my edit permissions. No. How do I... Okay, whatever. Man, this technology is too complicated for me. Too low IQ. I feel like I should just prevent the bot from joining this channel, but I don't know how you do that. Okay. Okay, sorry, back to math. Okay, I'm trying to draw a hexagonal grid. So there's like a hex grid, and then supposed to draw. Everything inside is colored green. Okay, I'm really bad at drawing this. Wait, that's not a hex. This is a triangle grid.
Yes, it's not.
I was like, why does this not look anything like the notes? Oh man, I'm gonna have to. Okay. Oh my god. Okay, I give up. We're just gonna use the one that's provided in the thread. Shout out to my boyfriend K2 from XKLEZH. Okay. Okay, that's too big, too big. Oh, this stream is dust. Okay, so you have a hex grid, and then some of them, it's a little hard to see in this picture, but the ones that are completely inside the loop are colored green, and there's some number of hexagons. So you want to prove a plus b plus c is even. So we're going to use like this theorem from Euler. This theorem says that if V is connected, if G is a connected graph. I stress that this actually requires a connected hypothesis. People often forget this. Connected planar graph. Then V minus E plus F equals 2. Which seems like it might be useful here because, well, I mean, the problem has components and edges and faces. Okay, so, right. So in particular, if I look at a bunch of green edges, the number of faces corresponds to like, if I look at just one component, the number of green hexagons is, each green hexagon is a face, but then there's also one unbounded face. So F is always equal to 1 plus the number of green hexagons. And of course, E is the number of green edges. On the other hand, the graph has an interesting property. It has the following claim. For every vertex, the degree of the vertex is either 1 or 3. Like every vertex is a 1 or 3 degree. And this is true because, I mean, you can just kind of look at it. Like, if you have a green edge and then another green edge, it's impossible for there to be just one edge from the loop out here. Okay, so in particular, all degrees are odd. And whenever you have a graph where every degree is odd, the number of vertices is always promised even. Cool. So consequently, when I sum across all connected components of this relation, it will promise me that some random even number, even minus b plus a plus c is also even. So a plus b plus c is even as desired. All right. Yeah. Okay, cool. Man, I think I've spent longer like dealing with random things than actually doing math. Okay, fine. All right, last problem.
Wait, I can't this.
Oh, right, sorry, yeah.
Yeah, okay. So when I originally was trying to okay, let's try combo, right? And so of course, I was thinking, okay, let's try a grid combo. The square grids got boring, and I honestly I've never solved a square grid problem, ever. So I decided that's too hard. I'm gonna mess around with the hex grid, and I just sort of drew some closed loops, and I for small closed loops, the number of edges was always odd, and I thought this was really strange. I was like, wait, how is this generally true? This has got to be false somewhere. And so I tried to find something with symmetry, right? Because symmetry would probably break it. And so it turns out that what I tried was an internal hexagon. I actually had an internal hexagon, and then 6 little edges sticking out of it. That was the thing inside the connected component. And so that turned out to have an even number of edges, but it had a hexagon. And so then I was like, okay, if I adjust for the hexagons, is the parity of this thing preserved? And it happened to be. And so yeah. Also, if you didn't see what I said in the chat, my initial solution was not this graph theory solution. This graph theory solution is extremely elegant. My initial solution was the induction solution that involves deleting hexagons slowly until you sort of make it one thing. So yeah, that's all I really have to say.
Yeah. And the proof that v minus e plus f equals 2 is typically done by induction as well. So sort of it's not surprising that given this proof that induction solution would also just be straightforward. Cool. Yeah. Yeah. Okay, so let's do the polynomial thing. Cool. So let me first tell you what the answer is. Shout out to Yas Ivy from LMAO. I feel like I'm missing some context, but okay. Okay, so c equals 0 works because you can let p of xy equals x plus y. Freaking. Sorry, not this is c equals 2. No, c equals 0 for the sum. Right? No, hang on, what? C equals 2 for gives x plus y, c equals 0 for x squared plus y squared. So I should say first of all that you can actually classify for the values of C that do work all the polynomials that work. But because I don't want to lose too many people, I'll probably do the more lowbrow thing and just find all C which work. But this is the solution. This is like the values of C that do work, plus an example for each of those values of C. Shout out to, did you know that John 0512 got a 46 on MathCounts chapter? Is y minus x? Yeah, y minus x. Why did I have my y squared minus x word here? Man. Yeah, y minus x. This is wrong in the solution I printed out as well. So for contest organizers, if you haven't fixed that typo yet,
Wait, y minus x does not work.
y minus
It will
x
give you x squared plus y squared minus 2xy equals x squared plus y squared plus 2xy.
So that's y squared minus. Okay, wait, I'm going crazy. It is a y squared minus x squared? Sorry, you're right. But if I do y squared minus x squared, 2x4, y4.
If you do y squared
Okay,
minus
yeah,
x squared,
yeah.
it gives you something like minus 2x squared y squared on both sides.
Okay, I'm rejecting that shout out. Thank you, Justin Lee, 2017A for the follow. Okay, so let's actually prove that these are the only values of C which can work now. No, it's y squared. Y minus x does not work. It's y squared minus x squared. Okay, so first claim P is is it homogeneous or homogeneous? I never know. I'm gonna say homogeneous. Homogeneous. I.e., like all the terms of P are of the same degree. And the reason is that if this is not the case, so suppose that P is like a term of. So suppose P is like a degree n thing, and then plus like a degree k thing where k is less than n. So what happens when I expand? So let's let this be like the second highest degree. All right. Then on the left, p squared, when I square it, will be, you have like a degree n thing plus 2n, degree 2n plus degree n plus k, right? And then some trailing order terms. But when I look at P of cxy squared plus y squared, the leading things are degree 2n and degree 2k. And this thing does not match this thing. So this is bad. Okay, so P is homogeneous, which makes our lives a lot easier because it's sort of homogeneous two-variable polynomials are really just one-variable polynomials that are more symmetric. So this will help us a lot. So claim P homogeneous. Okay. I'm going to bump some people up. Dun, 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 dun. And Epic X Troll 3. Sorry, DJ, I keep making you wear the moderator hat. Yeah, I had the feeling that you might not want to do this, but unfortunately, I actually can't keep track of too many things at once. Okay, cool. Right, what was I doing? So, to make our lives a little easier, we are going to actually make it into a 2-variable polynomial. So I'm going to say, sorry, 1 variable. So I'm going to say x doesn't divide p of xy. Because if it did, then left-hand side is divisible by, let's see. If e is the power of x in p, then the left-hand side is divisible by x to the 2e, whereas the right-hand side is divisible by, is it x to the e exactly? Can't get higher than that. So you get the cxy, and then the x squared plus y squared will mix in. Yeah, so this is exactly. So 2e equals e implies e equals 0. So what that means is p is basically a bona fide 1-variable polynomial now. So minor claim, x doesn't divide p. And what happens is now we can basically think of p of xy as, so let's see, I can divide out the, yeah, there's a y to the n coefficient. Okay, so it's like x to the n times like y of x to the n plus some other blah. It's a basically it's like x, you can think of it as x to the n q y over x, where q is degree n 1-variable polynomial. Okay, cool. So what can I do with this? So let's actually go back to the original equation in a little more substantial detail. We have like x to the 2n q of y over x squared is equal to like q, I'm gonna get this wrong, x squared plus y squared over cxy to the n times like q of, this sucks. Do I want to do it this way? No, I don't. Let me backtrack a little. Let's decompose cos q first. So we can write q exactly as a polynomial. Without loss of generality, you can assume it's monic because the, oh no, you can't. Never mind. That's okay. Well, let q be like some constant k times e minus alpha I for the complex roots. And so now, when I put this in, it's sort of like, you can sort of imagine just setting x equals 1 and y being z. Because, you know, more or less, once it's homogeneous, we will basically, you can basically treat it like it's a 1-variable polynomial. And what that tells you is that p of z minus alpha I squared times this constant k is going to be equal to the product of z squared minus alpha I c z plus 1 is, I believe, what you get, times k. So this is sort of, yeah, this thing is like x squared plus, this is the x squared plus y squared over xy comes out to this. So it's like, you can sort of imagine setting z equals y over x, and you'll see why this is true. Because I'm just plugging stuff in directly like this. Okay, great. So now I'm looking at this and I'm like, okay, well, you know the left-hand side completely. Like, you know all of the roots. So I should be able to pinpoint a lot of stuff. So specifically, let's look at, suppose alpha is a root. Then it should be a root of some factor on the right-hand side as well, right? So if alpha is a root, then maybe it divides like, then yeah. It should divide one of the other terms on the right-hand side. So it's like alpha squared minus alpha c beta, sorry, let me do beta c alpha. Equals 0 for some beta, which is also a root. And what that means is, well, I can write explicitly what beta is, right? So beta is equal to alpha 1 over c times alpha plus 1 over alpha. So TLDR is that if alpha is a root, then 1 over c times alpha plus 1 over alpha is a root as well. So that's pretty good. But we can say more because we actually have a multiplicity statement, right? Because alpha is not just a root of the left-hand side, it's also a root of the right-hand side. Or sorry, it's like double root times more stuff. So specifically, if I pick, let's say pick this one to be the most common root. Let me say most frequent or something. So i.e. the one with the highest multiplicity. Then, well, every time I have it as a root, for every factor on the right-hand side it divides, it could divide it doubly, but let's see. So let's like z minus alpha. You have some number of these, right? They come in pairs. And then you have these z squared minus beta z times cz plus 1 terms on the right. And each thing could stuff up to 2 of them. But, you know, this thing will give you one of the roots is beta. This thing will give thing. So my claim is that, in fact, every pair gets stuffed, like the way I'm saying. Because if not, what happens is... let's see. Like, you can, you know... If this happened and they split... So I'm just dropping indices because I'm being sloppy. But this would mean that 3 of the alpha i's are equal to the most common alpha, which would mean that actually this should appear 6 times rather than just 4 times, as an example. So by counting the multiplicity, what happens is, in order for, when I look at the most frequent root, it must actually doubly divide on the right-hand side, each thing. So this shape can't happen, and in fact, when I have the beta like this, in fact, this must exactly be equal to z minus alpha squared. Yeah, that's the only way it could happen. Why is it z minus alpha I squared? Because on the original problem, p of xy is squared. Alright, so what does this mean? Well, it tells us that alpha is plus or minus 1. Because you compare it to the constant term. And so beta must be plus or minus 2c. However, if you put this 2 and 2 together, you start seeing something, which is I proved that I picked any alpha with maximal multiplicity, like appeared as many times as possible, and I found that it's plus or minus 1. This beta is also a maximal root. So if I repeated the same logic to it with, like, say, replace the alpha with beta and the beta with gamma or something, you would find that this also has to be plus minus 1 by repeating the argument once. And so plus or minus 2 over c is equal to plus or minus 1. And so altogether, this gives you c is equal to plus or minus 2 Uh-oh, what did I do with 0? I'm sorry, shame on me. I divided by 0. Okay, that's where it went. Because I was like, there's 3 answers. Where'd the last one go? Yeah. This step here assumes that C is non-zero because I'm dividing by 0. Yeah, shame on me. Dividing by 0. That is very sloppy of me. Okay, anyways, that's it. Alright, that concludes a nice review. Anything from the...
Yeah, so I'd just like to speak a bit. So obviously Nikolai is not here, and I would be surprised if he was, frankly. But here are some comments from us on this problem. So when we first got this problem, which was around actually the end of 2020, we all just were like, this is too hard. And then we never really got around, or no one in our committee actually got around to solving the problem. It apparently did appear for some TST reviews. So Ankan, for example, had seen the problem before, but it's not like any of the rest of our committee has solved it. And then fast forward, we put it on the test. Still, there are like only the official solution and Ankan's written up version of the official solution. And then on March 26th, for some reason, Nuke Launcher and I decide to both independently try the problem, and on that day we both succeed, find 2 different solutions completely independent. So it's a problem that went unsolved for 4 months, and then in the span of 4 hours got 2 solutions. So it's a really interesting problem. I do think it's fairly hard and deserves a number 4 spot, and we would like to thank the 2 authors, Nikola Beluhov and Konstantin Gera, for proposing the problem to NICE.
Alright. Okay, so that concludes tonight's review. We'll be back next week with the same program and more moderators.